Okay, here we're going to talk about cylinder and quadric surfaces. Now, a cylinder isn't just, in this case, isn't just like what you think of, a can. Other shapes are classified as cylinders, so let's get right to the definition. If you have a curve C in a plane, and L is a line not in the plane, then the set of all points on all lines that intersect C parallel to L is called a cylinder. Now this looks like a complicated definition, so let me draw a picture. Okay, here's a flat plane. Let's just let it be like your desktop. And here's a curve in the plane. And let's just put the line right here at the edge of the plane. But the plane, you know, goes on forever, infinity. Okay, let's let that be the curve. Then all these lines that intersect the plane parallel to that line, and again, these go to forever, infinity in both directions. So that object, it's like a curved piece of paper standing straight up, in this case, that object is called a cylinder. This is the curve C, this is the curve L. And actually, L is called the directrix. So, I mean, even if you have, and I'm just drawing it flat, the plane can be anywhere. I mean, you had a circle, you see if you had all these lines parallel to that line, I don't draw very good, but you would get this, what we think of as a cylinder. But this is, the one on the left is also called a cylinder. Okay, let's talk about a trace, because these are going to be important to help us graph these things in 3D. The trace of a surface is the intersection of the surface with any plane. We're going to take our traces to be parallel to the x, y, x, z, and y, z planes for our cases. Okay, and these are going to help us sketch it. So let's look at an example. Let's look at z equal x squared plus y squared. Now, it doesn't matter which one you do first, but let's look at some of the traces. If we let x equal 0, we're in the yz plane. And then we have z equal y squared, which is a parabola. So here's y, here's z. Again, we have to remember this is 3 dimensions. X is coming out straight out at us. We get this parabola. Okay. If you let x be any constant, then we're parallel to the yz plane. We're in the plane, any plane parallel to the yz plane, and we still get a parabola. We get z equals y squared plus k squared. So we're just shifting the parabola up. So you're still gonna get parabolas shifted up. If you let y equals 0, we get the trace in the xc plane. And again, we get a parabola. And this time, x is coming out at us, so let me erase this. X is coming straight out at us. So we're in the xc plane. It's going to be flat again in that plane. And then if we let y equal k, we get all the planes parallel to that. So we would get parabolas coming out, just shifted up like that. Now, if we let z equal 0, then we have 0 equal x squared plus y squared. We just get the point 0, 0, 0. And if we let z equal a constant, we get x squared plus y squared equals z, which are circles. So, let's draw the finished product. I have the flat parabolas, and then I have the parabolas coming straight out at us. And then I have circles here in the plane. And what we have is called a circular paraboloid. So it looks like a cup, and it goes to 0, 0. Okay, let's look at quadric surfaces. The general equation is where you have the term squared. Okay, this is how we're usually going to see them, but you can also have xy term, a yz term, an xe term, and a constant. And usually we won't see those. The axis will be rotated if we have constants for those. So we're going to try to graph y squared minus x squared equals 16. So if we let x equal 0 to get the yz plane, what it looks like in the yz plane, we have y squared equals 16, or we have y equals plus or minus 4. So we just get 0 for z can be anything. So let's just say that's a constant. And 0, negative 4. Okay. So in the yz plane, we don't we just go 1, 2, 3, 4. Z can be anything. So we just get these lines at 4, -4 in the YZ plane. Okay, if we let y equal 0, we get -x² equals 16. There's nothing in the xz plane. And z can be anything because it's not even represented in this equation. So when z equals k, we're parallel to the xy plane. We get a hyperbola, and the vertices are 4 units. So let me erase this. Remember, this is x, y, z. So we have these hyperbolas on the y-axis, and z could be anything. So if you move up, you still have the hyperbola, and you keep moving up. So it's kind of like a sheet that's curved. And this is the y equal 4 line. So I didn't draw this very good. And this is the y equal -4 line, and they're touching here. So they're curved sheets, and each of the traces is a hyperbola. Well, the traces in the xy plane is a hyperbola. So there's an example of one of these graphs. All right, now these graphs can be, of course, drawn in Maple, which I'm going to show you in a minute. I'm going to use Maple to draw a lot of these. And they can be classified, and they have names. And you can tell what they are just by looking at their traces. So the first one we're going to look at is an ellipsoid. Well, let's look at some examples first. Let's see. Let's go to Maple. And let me see. I want to make sure I get my examples right. Let's look at the example here. Notice I have with plots, so I'm going to execute that command. And then in order to plot these, if they're not solved for z, this one's solved for z actually, but the command you're going to use is implicit plot 3D. Put your equation in, and then put in your x, y, and z domain and ranges, and let's see what we get. And the neat thing about this is the one we just looked at, is you can spin it around and turn it around and look at it, and you see that the traces here are circles, and you see as you spin it, the traces are parabolas, and you can see you can see the actual traces here that our parabola is shifted up and down. So Maple does a real good job of showing us what this looks like. Okay, so that's the example we just finished. Okay, now Maple classifies these. We can classify them and we can draw them in Maple. Maple doesn't classify them, but the first one's an ellipsoid, and the general form is where all the variables are squared. So let's look at what this looks like in Maple. I think that's a 6. Okay, we're going to go to this one. So again, we have with plots. We have x squared over 4 plus y squared over 2 plus z squared over 3 equals 6. So let's execute that. And you can see, as you turn it around, that it looks like an egg. So the traces of this are ellipsoids, each one, and there's ellipses or circles. So you can spin the graph just by using your mouse and seeing what it looks like. So that's the first example, or first classification. Okay, the second one looks like z squared over c squared equals x squared over a squared plus y squared over b squared. And we call this a cone. So we're going to bring everything over to one side. We're going to do z squared over 3 minus x squared over 4 minus y squared over 2 equals 0. Let's look at that in Maple. That's this one. And you see we have actually two cones meeting here, and you can turn this around and view it from all sides. So you can see the traces. Some you have an ellipse as a trace, and you have planes as a trace, or lines as a trace. So this is what we call a cone. When everything's squared, but two of the variables have negative signs. Okay, let's look at what we call an elliptic paraboloid. This is where I have one of the variables is not squared. So I'm going to look at this example. Let's see what that looks like. So here we go. In the example we did before, we called it a circular paraboloid because one of the traces in the parallel to the xy plane were circles. Here, they're ellipses. If you notice, that's an ellipse. And again, you can spin it around and see the parabolas as traces and the ellipses as traces. So Maple's a really nice tool to see these pictures. Let's look at the hyperboloid of one sheet. Hyperboloid of one sheet. Now, in these general forms, like in this one, the elliptical paraboloid, it doesn't just have to be the z that's not squared. It could be the x that's not squared, and then the y and the z are both squared. So as long as one of the variables is not squared and they're all positive plus signs, then that's what it's going to be. And in this one, notice the z is negative, the z squared term is negative. Well, it could also have the negative x squared as long as the y squared and the z squared were positive. So this just has one of the square terms being negative. So let's see what this looks like. And again, we're going to use maple. And see if we spin this around, we have an ellipse. So the ellipse is one of the traces, and it's kind of like a funnel, two funnels put together. So you see the hyperbolas are as traces, and you see the ellipses as traces. Now it's kind of cut out here on the ends because I didn't set the ranges exactly right to get all these points, but you can get the idea that it does have an open center as you spin it around. Okay, let's look at hyperbolic paraboloid. Okay, one of the variables is not squared, and there's a negative sign. Okay, so let's look at this example. This is called a saddle. This is probably the neatest one. I really like this one. You have a parabola, you have hyperbolas as traces, and again, it looks like a saddle. But that's pretty neat. You can move it around and look at it, maple, and twist it around. That's called a hyperbolic paraboloid. And then finally, we will have something like this. It's called a hyperboloid of two sheets. And this is where two of the square terms have a negative sign. Again, it doesn't have to be x and y. It could be y and z. That means it's just going to lie on a different axis. Okay, let's sketch that and see what it looks like. Okay, see how these are not connected? And there's hyperbolas as traces and ellipses as traces. So going horizontally, you have ellipses, and vertically you have the hyperbolas as traces. So let's get to an example and see how we can sketch this. Now the traces should tell you what shape you have. I mean, it's not too hard to figure out, so I don't expect you to memorize all the different types, but you should become familiar with them so you know what to expect. Okay, we're going to sketch this one. We're going to divide everything by 144. So in the xy plane, z is 0. So we get x squared over 9 minus y squared over 16 equal 1. We get a hyperbola. Okay, and I'm going to try to sketch these as best I can. On the x-axis, we're going to go 3. On the y-axis, we're going to go 4, make a little box. So it's kind of a wide. Now this is laying flat on the xy plane. Okay, the yz plane, if we let x equal 0, we get z squared over 4 minus y squared over 16 equal 1. So here's yz. We're going to go up to on the z. It's going to lie on the z-axis. And it's going to be wide because it goes out 4 on the y-axis. So we have that. And then when y equals 0, that's the xz plane. And we get x squared over 9 plus c squared over 4 equal 1. And those are ellipses. So we have two hyperbolas and an ellipse. And the ellipse on the x-axis, we're going to go 9. And z is 2. So they're going to go like that. So these are, let's try to put all this together. That's why I'm going to use maple, because you'll be able to see it better. Okay, we have ellipses there, we have hyperbolas here, and we have hyperbolas here. So let's go and look at what maple tells us this looks like. I've typed it in. Again, I use the command implicit plot 3D, and remember you have to use with plots to start. And here we have a as you can see, I have hard time saying these words, hyperboloid of one sheet. And if you turn it around, you can see the ellipses, and you can see the two hyperbolas, the traces. And I know that looks nothing like my picture, but you can kind of see from the traces what you're going to get. And this is going to be a hyperboloid. Of one sheet. Okay, so in your homework, you need to try drawing these pictures and at least draw the traces and try to figure out what you're going to get. Then if you want to, you can check it on Maple, but don't do all of it on Maple. Make sure you're going to be able to find all the traces, because they will ask you how to find the traces.